Good morning. Could you please close the door? Thank you. So, today there's a new handout, which in part is the old handout concerning the probabilistic properties of excursion set features. The first part are these expectations, which we already discussed. I hope I corrected some of the typos, maybe not all of them, but at least some. And then there is a new part, probability distributions, which we want to discuss today. And in the end, there are now 6 study questions, and they are actually good for active participation, but next time, not today. So next time, the people who are here have already passed their active participation. The other ones, don't know what's up with them, but next time would be a good opportunity to check or cross out the active participation for those who aren't here. Good. Then we are still talking about the probabilistic properties of excursion set features, and let's get started with that. So we have to, let's first put down the title, probabilistic features of excursion sets. It's a little shorter. And of course we are still talking about excursion sets of random fields which model the null effect of no activation anywhere in the brain, so nothing has changed, of course. And we still have in 1D this same visualization where we have space, and we are still can draw realizations of our random fields, something like this. I'm not really getting better at drawing these realizations. And we still have the thing that we consider a threshold value u, or a level, or whatever you want to call it, which defines the excursion set. And based on the definition of the excursion sets, which is a space, or a subset of the search space S here, we have been discussing some of the probabilistic features. So I want to briefly revise the expectations that we have discussed, also to bring up the denomination of the random variables again that we use, and also we'll use more in the following today. So in terms of expectations, again under the null hypothesis, so that the expectation of the random field, of which you here see a realization is 0 everywhere, the expectations of these features were the following. So we first looked at a random variable which represents the volume of the excursion set. So remember, the excursion set is this subset of the search space for which the random field exceeds or is equal to, maybe this we can also include here, the threshold u, so it depends on the threshold u. And then we discussed last time the volume of this. So essentially, if you think of measuring these two black things. And we discussed a formula for that, and this formula was dependent on how the search space in total is actually measured. And we discussed that we can either use the Lebesgue measure, this is what you find in the Adler book, or we can use this third order Riese volume, which is used in the SBM implementation. And I think there were some typos actually in that part. So to clear that up, I now define a random variable VU, which models the volume of the excursion set. And this can then either be, depending on how you measure the volume, that can either be the Lebesgue measure of the excursion set, or it can be the third order Riesel volume of the excursion set. Just so that I can actually talk about this Adler proof on the Lebesgue measure. And then we've seen that the expected value, and this is what we were interested in, the expected value, the expectation of the excursion set at level U is given by, if we use this third order, if we use this third order Riesel volume, then it's given by the volume of the search space times 1 minus the distribution function of this test statistic evaluated at U, which makes sense because it's kind of the proportion of the search space for which the random variables take on a value larger than U, because this is kind of the complementary cumulative distribution function. So that is something that we've discussed. Then we discussed a random variable called mu, which models the number. So for number, use this hashtag, the number of local maxima, for which we discussed as expectation the approximation by the expected Euler characteristic of the excursion set, which in turn is given in this closed form. It's so annoying to write here, maybe I should do it like this. Which is given in this closed form that is this sum over the products of these Euler characteristic densities times the Riesel volumes of the search space. So this is what we discussed. In the script it's the other way around, but that doesn't matter. And then we discussed in the same regard, we discussed CU, which is the number of clusters. And we discussed that the expected value of the number of clusters is the same as the expected number of local maxima under the RFP framework. So this is an assumption or heuristic. And like the approximation by the of the number of local maxima by the Euler characteristic, it's also a heuristic or an approximation. But that's how it's done in RFP. And finally, we discussed a random variable that was called KU. So this is usually referred to as the cluster volume. I think once I'm through with the whole thing, I will call this the expected cluster volume, because it's not really clear to which cluster this actually refers, and it refers to all possible clusters, and hence the probability for a cluster being a certain size is actually the expectation of a cluster being a certain size. So that's cluster volume. For now I call it cluster volume, but if you start thinking about it, then you start to wonder which cluster is actually meant. And this cluster volume random variable was defined as the ratio between the excursion set volume, VU, divided by the number of clusters, which makes sense. So if you think you have like a I don't know, 1 cubic meter of excursion set, and you say there are 10 clusters making up this excursion set, then of course you would divide this 1 cubic meter by 10, and then you have the cluster sets if they all have the same size. But this is the assumption that these things are independent, and also that they have the same size. This goes into the direction of an expected volume actually. But this then, especially if you assume that these two random variables VU and CU are independent, directly allows to evaluate the expected cluster volume as the ratio of the expected volume of the excursion set divided by the expected number of clusters. So this is basically what we've seen so far, and we didn't do this just for fun. Of course we do the whole thing just for fun, but we need these things. So the VU, the volume of the excursion set, the number of local maxima, but actually more the number of clusters, so CU, and the cluster volume, we will need that a lot today. And yeah, so yeah, try to be clear about these things. This is what we have seen in the past, and now we have to not only talk about expectations of these features and say, okay, the expectation for the number of clusters, let's say, is 10, and we have observed 20 in our SPM analysis, so that's unlikely under the null hypothesis. So maybe these things are meaningful. To be a little bit more precise, we of course also need the probability distributions and parametric forms of them, so that we can say the probability of observing this, and this is under the null hypothesis 0.8, so it's not surprising, or the probability of observing this under the null hypothesis is 0.001, so it's unlikely, and say, oh, that's meaningful. So we need probability distributions to make these claims, as I discussed at length previously, like in the like for the T distribution. And the ones that we need and that we need to discuss and want to discuss today are the following. So first, the distribution of the global maximum. Why we need this? Really, this will only become clear once we talked about the multiple testing problem, but we can nevertheless discuss its distribution now. Then we need the distribution of the number of clusters. Currently we only have the expected number of clusters, but we now need a full distribution of the number of clusters to make these kind of p-value statements. Then we need the cluster volume. Again, for now we only have the expected cluster volume, but we now need a distribution over cluster volumes under the null hypothesis. And what else? The number of clusters of given volume. We primarily need this because of the idiosyncrasies of an SPM, number of clusters of given volume, because this is actually used to evaluate all the p-values in the SPM table. And fifth, we need the distribution of the maximal cluster volume. 4 and 5 might be reversed, so maybe it's more sensible to first talk about the maximum cluster volume and then about the number of clusters of a given volume. I'm not really sure on that yet, but my preparation is better for 1 to 4 than for 5, so I hope time runs out before we get to 5. I can talk about it, but it's not as good as the rest yet. Yeah, so these are the probability distributions that we need, and once we actually have them, then we actually know what's evaluated in the SPM table. And so I'm going a little bit back and forth whether we directly go after this to the SPM table or we put in a section on multiple testing, which I have prepared already, because one thing is what these things are that are evaluated in the SPM table. And this is what we basically discuss, and once we have discussed this here, we have essentially discussed that. But then, of course, the other question is why, for example, the global maximum is so important, or the maximum cluster volume is important. And this, of course, goes into the question of controlling for multiple tests. And I'm not really clear of whether we first do multiple tests or first do SPM table. Let's see what I decide over the week. Good. Any questions? So we are now basically starting, as we are almost complete. No? No questions. Good. Then let's go. So we have to basically work over these 1, 2, 5. So, first, distribution of the global maximum. So the first question when we talk about these distributions is, of course, the distribution of what actually, and so we have to define the random variables that we actually study. And so we have to, if we talk about the distribution of the global maximum, we first have to know what we mean actually by the global maximum. No? So to this end, think again of our random field, and remember that last time we discussed that there are, we now know different or a number of random fields, for example, Z fields, T fields, and F fields. All of these are now defined, where Z fields are, of course, just Gaussian random fields with expectation 0 everywhere and variance of 1 everywhere. And our general notation for random field is still this x thing, as discussed at length in the beginning. So assume we have this random field, and then we define the global maximum, very straightforward, as a random variable xm, which takes on the maximum value of the random field over its search space. Yeah. Oops. So of course you need to appreciate that this thing here is random, so that if you take the maximum of something that is random, you get something, of course, if you have a given realization. But if you obtain multiple realizations of the thing and then get the maximum, also this will be random. Yeah. So for visualization of what this means, this is a realization now, and then the maximum of this is, of course, at the location where the highest point is. But remember that there are two things. One is the maximum and one is the argument of the maximum. We are here interested in the maximum, so this value on the y-axis, that's our xm in this realization. And just to make clear that this is a random thing, if we get a new realization, for example this, then the global maximum of this, if global means until here, so this is where we stop looking, then the global maximum is of course here, and you see that it depends on the realization, so it's a random variable. The motivation for talking about the global maximum is actually strongly related to the question of multiple testing. So historically, talking about the distribution of the global maximum was actually one of the first things in the whole RFP framework. So that was introduced by Worsley in 1992. This is, and we will see why later, this is the corrected p-value at the peak level in the SPM table. Why it's a corrected p-value we have to discuss in some length, but it's still being used. So to ask what is the probability of observing this or higher, for example, t-value under the null hypothesis, to this end the global maximum distribution is still used. It's the peak level corrected p-value, whatever that means. We will discuss at length. Today we only discuss what its distribution is, and actually the distribution of the random variable xm is specified in terms of its distribution function. So remember that you can specify probability distributions in many different ways. You can, if you have a discrete outcome set with finite values, you can define a probability mass function very easy by allocating 0.2, 0.3, 0.5, and then you have specified this. You can use probability density functions like we did last term a lot with the Gaussian. And you can, of course, if you have a probability density function, you can also, instead of specifying the probability density function, you can specify the cumulative density function, which you are also familiar with if you did undergrad psychology statistics, or at least you should be. The distribution of the global maximum is easiest specified in terms of its distribution function. Remember that we also discussed what distributions functions are. I've updated that a little bit in the script, so if you look at the script that is available to you, there's a little bit more on distribution functions now, but essentially it's the same. So the distribution function of the global maximum under the RFP framework is defined as follows. So it's a function that takes in a real value, which for the moment we call u. U is mapped onto a value of the distribution function. And the distribution function takes on values between 0 and 1 because it refers to the probability that the random variable xm is smaller or equal to this value u. And this is defined under RFP as 1 minus the expected, Euler characteristic. So the Euler characteristic will feature many times in this whole thing. Actually, one should investigate whether there's some double dipping with the Euler characteristic here. This distribution function actually only holds in the limit of high thresholds, and we will discuss why that holds. But if you look into the peak level corrected p-value in SPM, what this actually does is it has, based on estimating the real volumes and knowing the Euler characteristic densities, it can compute, based on the formula that we've seen, it can compute the expected Euler characteristic, and then for a given voxel you have a given value that you can put in here, and then SPM evaluates 1 minus the expected Euler characteristic, and this is how you get your p-value. Why this is a good idea, again, we have to discuss at length, but for the moment we want to discuss how it comes about, so where this, what's the idea behind this. And the important thing, and this is actually what we find with all the probability distributions for the RFP framework, these are not mathematically derived distributions in the sense that you have a probability distribution of the random field, you define a function on it like we did here, and then you use the principles of how to look at functions of random variables and evaluating their distributions in a mathematically rigorous way. That's not how the whole RFP thing is done. It's done using heuristic arguments, and the heuristic argument here is the following. Assume that the threshold is really high. What do you remember? We discussed that already. If you increase the U value, what will happen with respect to the excursion set? It gets smaller, yeah. And if you think about the things that make up the Euler characteristic, namely the number of connected components, the number of handles, and the number of voids, what will happen there? If you remember also the plots that I've shown you some time ago. So they get more separated. So essentially what happens is that the handles go away. So if you think about think again of like the Alps or the Himalaya, and you flood the whole thing with water because it's fun and it's climate change, then you especially the thing with the handles is then relatively clear, because handles are like enclosed things like lakes, but that are fully surrounded by mountains, if you increase this even further, the handles will go away because the clusters get separated, and then you get only connected components, so clusters as they're called in brain imaging. And if you only have connected components and no handles and no voids anymore, so voids is something we assume we not talk much about. So if you think about a cheese that has some voids, we are very high at the cheese where the voids are not there anymore. And if there are voids, then they are actually these excavations that you sometimes see at the side of a cheese. It's kind of when you draw cheese, you actually emphasize that this is cheese by drawing these kind of things. That's cheese. And if you then increase even more, so just going from having connected components even more, so what happens then? You said you decrease, and then what happens then? If you increase the threshold even further?
Essentially you have one.
Yeah, exactly. So in the very end, you only have the highest peak, like the Mount Everest, or if you increase even further, then you have none. And in this scenario, we are now talking, so where the threshold or the U value is that high that there's either one connected component, so one cluster, or none, then the Euler characteristic evaluates to what? If there's one connected component, what does the Euler characteristic evaluate to? 1. And if there is no connected component, exactly. So then we have 0. So this is kind of if we conceive the Euler characteristic as a random variable which takes on the values 0 and 1, then we can assign probabilities to them. Namely, of course, on the one hand, the probability that the Euler characteristic is 0, and on the other hand, the probability that the Euler characteristic is 1. And now the thing about the global maximum is that, of course, the one remaining cluster, if it remains, or the one remaining connected component, so the case that the Euler characteristic is 1, this must be the global maximum because it's the highest thing. So this then leads to this equivalence of probabilities that the Euler characteristic being 1 is the same, that's a heuristic argument, is the same as the probability for the global maximum to be larger or equal to u. Yeah? So if the Euler characteristic is 1, that means there is still one cluster in the excursion set, and this means, because this must be the global maximum, that the global maximum must be larger than the threshold. I mean, it's not that hard to imagine. And then, of course, the probability that the Euler characteristic is 0 is, in terms of the global maximum, equivalent to what? That the global maximum is 0? The Euler characteristic is 0. That also means that the number of local maxima is 0, yes. But what can you say about the relationship between the global maximum and the threshold if the Euler characteristic is 0?
Smaller than
U. Yeah, actually, so one has to decide. So I'm deciding here in this way. So one should consider one case where it's equal to only in one. Otherwise, it's not a clear case distinction. So we have the larger or equal to U in this case, and then this means it must be smaller. And here it's then smaller. Also, it must be smaller because if it's equal to, it's still there, so the excursion set still is not completely empty, and then the Euler characteristic is still 1. But of course, roughly that's exactly what you said, which is good. So we have now seen that equivalence, and now what we want to do is compute the expected value of the Euler characteristic. Maybe we've done this, it feels strangely familiar, but how do you compute the expected value of the Euler characteristic in this scenario when it only takes the values 0 and 1? How do you compute the expected value of a die?
It's a probability of 1. Because the other one is the probability of 0 times 0 plus 0.
Yeah. So can you say before that how you compute the expected value?
It's the value you can take on times the probability.
Mm-hmm. Exactly. And?
Or add it up the sum of all values.
Yeah. So we might want to, in this case, write it like this. I mean, one can do it. Let's write it like this. So what Lena just said is that we take the value and multiply it by the probability. And this is how you always compute expected values, of course. And then if we have the case of the expected value, the value of the Euler characteristic being 0, then we have 0 times the probability that the Euler characteristic is 0, which is 0, and then we add to it the value of the Euler characteristic 1 times the probability that the Euler characteristic is 1, which means that we get the probability that the Euler characteristic equals 1, which then is the same, because we discussed it previously, that the probability for the maximum is larger than U. So the expected Euler characteristic and the probability that the global maximum is larger than U are the same thing. Now the only thing that remains is if we want to express this as a probability, as a distribution function. A distribution function is actually defined as the probability that if you have a density that a random variable x is smaller than u. Yeah, so look again at the definition of distribution functions. So we have to, if we want to turn this expression into a distribution function, what we did above, we have to take 1 minus p xn larger than u. If you want a picture, so this is if you're dealing with density functions, what is written there is this bit. So that's the bit that I just crossed out. 1 minus is the rest. If you turn the whole thing into a density function, I always get that wrong, as Sebastian will be able to tell you, then the probability that the random variable takes on a value smaller than something is this here. So here you have your x value, and this is the probability that the random variable is smaller than x. This is, we can remember that because this thing always goes up to 1, and at one point, if you're very high value of x, then this is the probability that the random variable is smaller than this value of x is always 1, so one can remember that. So because it's plotted this, if we have this, we have to do 1 minus this. Please clarify that again for yourself by learning about distribution functions. It's really simple, but one has to carefully check again. But it's just the definition of distribution functions, which means if we have this, we can simply turn this into a distribution functions by doing this, which is then also, because this and this is the same, 1 minus the expected Euler characteristic. Yeah? So that's the heuristic argument to come up with this distribution function. Yeah? So this is the distribution function, and I just presented the argument. And as you see, this only works really, and this argument only works if the threshold is that high that either the Euler characteristic is 0 or 1. Yeah? If we're in a different scenario, this whole thing doesn't apply. This is why there was some discussion on the height of the threshold. Good. Questions about the distribution of the global maximum right now? Why we need it? I mean, I already told you that this is the corrected peak level p-value in your SPM table. But why this actually controls for multiple testing, in which sense we will discuss later. Yeah? But you already know something about the SPM table now, so please appreciate that. So go to your supervisor and ask them, so what exactly, how is this p-value corrected for the peak level? And then you say, well, it's computed like 1 minus the expected Euler characteristic. Maybe you pronounce it, you practice how to pronounce it first, and then you go to your supervisor. Good, so first thing done. Number of clusters we can actually do before the break, because that's relatively quick. So 2. Distribution of number of clusters in the excursion set. Yeah. So the question is now, we have an excursion set. How many clusters do we have? And that can be either 1, so that's one excursion. So an excursion set that has that has only 1 cluster, sorry, or you have many more clusters in excursion set, which are all separated, of course, and then you have more. You cannot have 0 clusters in an excursion set, because then your excursion set is actually empty. Yeah? Or they're going a little bit back and forth. So the problem is there is not a full mathematical model, and I'm currently wondering whether if you have 0 clusters, whether that means that you have a lot of clusters of volume 0, or you actually have 0 clusters. It's more a philosophical question. No, it's not. Actually, it's not a philosophical question. It's if you really write up a really well-defined probabilistic model, then these kind of questions are important. The distribution of number of clusters. And there, what we have already discussed is the expected value of the number of clusters. Yeah? And we've seen that this is the same as the expected number of local maxima, and that this is the same as the expected Euler characteristic. So this is what we know already, but the question is how is this distributed? And there's actually there is a result there's a theorem by Adler 1981 which discusses theorem 6.93, which discusses a specific Euler characteristic number, which is a little bit involved. So I don't go into details about that. But what Adler then writes about this Euler characteristic number, he writes that this number is essentially the same, as the number of components of the excursion set. And because the number of components in the excursion and the number of local maxima above U, and since these are essentially the same numbers, they should essentially have the same limiting distributions for high values of U. And then he writes, this, however, has never been rigorously proven. Yeah. Now, Friston, 1994. Basically reference this theorem, which says that the number of clusters in an excursion set is distributed according to a Poisson distribution. So I hope you studied Poisson distributions a lot over the last week, because last week we discussed what Poisson distributions are. So does anyone remember what the parameter of a Poisson distribution is? Lambda, yeah, that's a letter that one can give to the parameter, but what does this lambda intuitively refer to? So if you think about a Gaussian distribution, you usually call the parameters, or I call them mu and sigma square, but they also have meaning. So what's the meaning of mu for Gaussian? And sigma square? Yeah, and in the same vein, what is lambda for the Poisson distribution? Exactly. This Poisson distribution here has a parameter, which I call lambda Cu, because it's the parameter of the Poisson distribution for the random variable Cu. And as you just said, the parameter of a Poisson distribution specifies the expected value. Now, we already have an expression for the expected value, namely the expected Euler characteristic, which, always remember that, is given in this closed form, namely this. Don't forget that we always have this closed form, which once we have the Riese volumes of our search space, we can evaluate. And so we have the expected value, so we can use our approximation of the expected value for the number of clusters as the parameter of this Poisson distribution. Yeah? Because then this Poisson distribution has expected value Cu, because that's what the parameter parameterizes, and we have an expression for that. Yeah? So what does this mean a little bit more intuitively? So Poisson processes are, you can understand them as things that happen independently over space at a given rate. Yeah? So Friston et al. Discussed that in terms of radioactive decay, which is a little bit confusing because radioactive decay is in a process over time. But you can imagine it like this. So you have, let's draw it. You have something like this, and then something occurs here. And then there is a given rate that something will occur next, but it's independent of that something has appeared here. It's just a probability that something will occur. Yeah? So there is basically, if something occurs here, it doesn't mean that now for some time nothing occurs, or that something occurs right between. There's just an average rate of occurrence. So let's say, how can one draw that? The average rate of occurrence is, let's call it 0.5 for the moment. Then you would get something like this. maybe, if you do realizations, and if you have a higher rate of occurrence, let's say 1.5, can also view it as that many occurrences over 0.5, then you need to invert it. But if you have a higher rate of occurrence, you will get something not too surprising like this. And again, the spatial layout, there's no dependency, but the rate of occurrence is higher. Yeah? So this is what a Poisson distribution does. And yeah, this is how it's distributed. The number of clusters. Yeah, so you what is interesting, at least from my point, is that this is again somewhat of a heuristic. So, as clearly stated by Adler, so this is has not been proven. The question is whether a proof would be actually be able to show that it's not the case. So sometimes proofs, even if they don't exist, they also don't help much if they exist, because then they just show that this is the case, what you knew all along. And this is why a lot of people don't like math, because they say then after you worked really hard to understand the proof, you're just back at the result and you say, oh, I knew the result even before, so why did I go through this proof? But yeah, so we have now a Poisson distribution for the number of clusters, which is just parameterized by the expected value of the number of clusters, for which we have this expression. And this is a good time point for a break if there are no questions right now. Good, then let's have a break.